Hey guys, welcome back to another video on projectile motion. I thought it might be better if I broke this topic into different videos so we could cover each scenario that I mentioned in the last video. So in this video, we'll take a look at the second type of problem that we commonly see, which is something I like to refer to as the complete projectile motion scenario, where an object starts and finishes at the same level. So just like before, we can break this motion up into two components where we're looking at the vertical velocity and the horizontal velocity, where the horizontal velocity remains constant throughout the entire motion and the vertical component of velocity is subject to gravity. So therefore, I can apply the constant acceleration equations of motion to the vertical velocity components because I know my gravity is going to be a constant acceleration downwards of 9.81 meters per second squared. Now there are a couple of unique characteristics about this type of a scenario, and one of them is that the vertical velocity will be zero at the highest point in the flight path, which will also be measured as x max from the ground, which will be the maximum displacement. So at this point here, we'll know that VV, which is our vertical velocity component, will be equal to 0. And this will actually be reached when we're halfway through our flight time. So this point here will be occurring at t is equal to half t total, which should make sense to us intuitively as well because our flight path is symmetrical. Another term that we want to be wary of when we discuss this sort of a projectile motion is called the range. So the range is the horizontal displacement that this object will have at the end of its flight path. So we'll call that r. And r is just equal to the horizontal velocity times time, where this time is the entirety of its flight path. So let's see if we can use these characteristics and describe this type of motion through using these equations. So let's assume that we have an object that's launched at some angle theta. So let's say the velocity is acting in this direction at some angle theta, and let's call this v, some velocity, and we have its horizontal and vertical components, which I've drawn in, where the horizontal component is going to be called v of h, and that'll be equal to v cos theta. We'll do the same for our vertical component, so we'll say VV is equal to V sine theta. And let's say we want to describe x max using these components. So if we're looking at the vertical direction, we know that the ball, or the object rather, is going to have a vertical velocity of 0 right at the top of its flight path. So I can go ahead and use my equations of motion and write down all my knowns and unknowns. So I know my initial velocity will be v sine theta. I know my final velocity will be equal to 0. I know my acceleration is going to be negative g because let's say I've considered up as positive. I know my x at that point is going to be x max. And I know my t is going to be half of the total time, and I'll represent that with a big T here. And let's say I want to derive an equation that's completely independent of the time, so I'm only relying on these four variables. And the only equation that kind of lives up to that is this one here. So I can go ahead and substitute all my values into that equation. I know my v squared will be 0, so I'll put a 0 there. I know my initial velocity is just going to be v sine theta squared. I know my acceleration is going to be negative g, so I can say negative 2g. And I know x is going to be my x max, so I'll put that in as well. Now if I rearrange this equation for x max, what I get is, I'll just take that to the other side, so I'll get 2g x max is equal to v sine theta squared. So I can manipulate this expression or this equation for x max to say x max is equal to v sine theta whole squared divided by 2g. And this expression here will give us the maximum vertical displacement that this object will experience over its entire flight path. So let's move on and look at one of the other characteristics of this flight path. Now, what if we wanted to express the total time taken for the object to hit the ground in terms of the other variables that we've been given? Well, we know that the total time that this object stays in the air will be twice as long as the time taken to reach the maximum point. And this is due to the symmetry of the flight path. So we can look at the vertical component of the velocity once again and see when it hits 0. So using these same values, I can go ahead and express them in terms of t. So I can use this equation over here to do that, where I'll say v is equal to u plus at. Our final velocity is 0, so I'll put that in. Our initial velocity is going to be v sine theta, and our acceleration is going to be negative g, and our time is going to be half t, where the big T is the total flight time of this object. And I can manipulate this equation to give us an expression for t such that t will be equal to 2v sine theta divided by g, where this will be the total time taken for the object in its flight path. What if now I want to find an expression for range such that there's no expression for t in that equation? Well, I can go r is equal to vh times total time, and I know the total time taken is equal to 2v sine theta over g, so I can say vh times 2v sine theta over g. And vh is just our horizontal velocity component, so I can put that in as well. So I can say 2v sine theta divided by g multiplied with v cosine of theta. And this will give me the range expression without having time in it. And I can simplify this expression to say v squared times 2 sine theta times cos theta divided by the gravity, which is g. And this here is actually a trig identity, 2 sine theta cos theta, but we won't go into that. That's more of a mathematical thing. For now, all we need to know is that you can rewrite that as sine 2 theta divided by g. So this leaves us with three pretty important equations, where the x-max equation describes the maximum vertical displacement achieved by the object without the term t, which is time, in the equation. Our second equation that we derived gives us the total time taken for the object to complete its motion. And our third equation here for r, or horizontal displacement, is the total amount of horizontal displacement achieved by the object at the end of its flight time. So let's move on and actually apply this to a question so you can see how this works a little bit better. Alright, so let's continue on with our question for this lesson. We've got a cannon that's set below ground level such that the launch point of the cannonball itself is located at the ground level, and the cannonball is shot out at a velocity of 45 meters per second at 30 degrees to the horizontal. Above the diagram, we've got the equations that we've derived from the previous slide, where our first equation calculates x max, which is our maximum vertical displacement, and I'll mark that on the diagram as x max. And it's important to note that at this point, our vertical velocity will equal 0. Our second equation over here will give us the total time taken to complete the motion. And our bottom equation will give us the range, or the maximum horizontal displacement this ball will experience, and I will label that as well. So we'll call this R for range. So let's begin part 1 of our question, which requires us to find the total velocity after 2 seconds. We can begin by breaking up this velocity into its two components, its vertical and its horizontal component. So I can go ahead and draw that as v, which is acting at 30 degrees to the horizontal meters per second, and I've got its vertical component, which is going to be 45 sine 30, and I've got its horizontal component, which is going to be 45 cosine 30, and I'll label these as VV for vertical velocity component and VH for horizontal velocity component. We know that the horizontal component is not going to change throughout the entirety of the motion, so that's going to remain constant. And we know the vertical velocity is going to be subject to the Earth's gravitational field, so we'll have an acceleration acting downwards of g, and that'll be 9.81 meters per second squared. Because the vertical component will be subject to a constant acceleration, we can go ahead and use our equations of motion, which, with the magic of technology, should appear on the screen now. And I've made a bit of a mistake in the notation here, so let me just fix that up real quick. So that'll be 45 meters per second, which is now consistent with what I've written there. Cool. So let's go ahead and continue with our calculation. Now, we're looking for the velocity, the total velocity after 2 seconds. Now we need to work out what our vertical velocity will be after 2 seconds, because we know our horizontal velocity is going to remain consistent throughout the entire motion. So what we need to find out is v at 2. We know our initial velocity is vv, so we can write that as vv is equal to 22.5 meters per second. And we need to find our final velocity at 2 seconds, so we can use v is equal to u plus at. So v is going to be v at 2 seconds. Our initial velocity is vv, which is 22.5 meters per second. Our acceleration is just going to be gravity, so that'll be negative 9.81 meters per second squared. And our t is going to be 2 seconds, because we need to find out what's happening with the velocity, or the vertical velocity rather, after 2 seconds into motion. So let's go ahead and plug those values into the equation. So we have v equals u plus at, so that's 22.5. Our acceleration is 9.81, and our time is 2. Which gives us our final velocity at 2 seconds, which is equal to 2.88 meters per second. So now if I want to draw out if I want to find out our total velocity at 2 seconds, we know our horizontal component is going to remain the same, so that'll be 45 cosine 30. I know our vertical velocity at 2 seconds is going to be tiny, at 2.88 meters per second. So our total velocity will be 45 cos 30 squared plus 2.88 squared, and we'll take the square root of that to find the velocity total at 2. So Vt at 2. And if I plug these values into the calculator, I get 39.08 meters per second. So let's move on to part 2 of the question, which says find the time that it takes for the maximum height to be achieved. And if I go up, I know that the total time it will take for this flight path is given by this equation here. So t is equal to 2v sine theta divided by g. And I know half of this time is actually when x max occurs. So I can go ahead and plug my values straight into this and find the solution. So I can say t is equal to 2v sine theta divided by g. And I can go ahead and plug in my values. So I know 2 times v, which is 45, and theta, which is 30 degrees. So 30 divided by our gravity, which is 9.81, will give us a time which is 4.59 seconds. And if you wanted to just like confirm this and do a bit of a sanity check, you could go ahead and actually plug it into the v equals u plus at equation, where we know the final vertical velocity is going to equal 0. So I can go ahead and do that as well. So I'll say v is equal to u plus at, where we know this is going to be 22.5, so u is 22.5, and I know our acceleration is negative 9.81. T is what we're trying to find, and 0 is going to be our vertical velocity at the maximum displacement. So I can take this expression to the other side and say T is equal to 22.5 divided by 9.81. Remember that the top equation gives you the time for the entire flight, so our maximum vertical height will be reached when it's half of this T. So half of T is equal to half times 4.59, and this will give us the time for the maximum vertical displacement. So I'll put that into the calculator to give me 2.29 seconds. And then I'll do the same calculus here to give us time of 2.29 seconds. So you can do a quick sanity check if you have a little bit of a mistrust of the formula that we derived. All it is just using the constant acceleration equations of motion. So before we move on, I might just label the answers to these. So this is question part 2, and this here is the answer to part 1. So let's continue on and let's see what our next thing is that we have to find. So what we have to find is the maximum height, and we can go ahead and use our x-max equation that we derived from the previous slide. So we can say x-max is equal to v sine theta whole squared, use a bit more space here, whole squared divided by 2g. And we already know all the values for this, so we know x-max is going to equal v, which is 45, sine 30 whole squared divided by 2 times 9.81. So we can go ahead and plug that into our calculator to give us 25.8 meters. And that would give us the maximum displacement that this ball would experience, or this cannonball would experience vertically. Now, if you were still in doubt and you wanted to do a sanity check again, you could go ahead and use the constant acceleration equations of motion to sort of confirm this answer. So we could say x is equal to vt minus half at squared. And we know at its maximum displacement vertically that the velocity is going to be equal to 0. The vertical velocity is going to equal to 0. So this term would go to 0. We'd need to find x, and we already know that the time at which this occurs is halfway through its total flight time, which we found before. So our acceleration is negative 9.81. And if you're confused as to why it's negative, it's because our coordinate system is set up such that the y is positive that way and x is positive towards the right. So we'll put a little plus sign there to signify that. And we know the t that we found before was just 2.29 from our previous question. So 2.29, and we're going to square that. And this here should equal this. So let's just go and put that into the calculator and confirm. And to no one's surprise, that gives you 25.8 meters as well. And I'll go ahead and label this question as well, because I don't think I did at the start. So that's part 3 of the question. Cool, so now that we've done part 3 of the question, let's move on to part 4, which asks for the minimum speed that will be experienced by the cannonball. Well, we know that the speed is the magnitude of the velocity, which will be made up of 2 components at all times, except for when the cannonball actually reaches the top of its flight path. And this is because the vertical velocity at this point will be 0. And beyond this point, the cannonball will begin to accelerate again due to the effects of gravity. So again, if we were to look at this point, we'd have a little bit of a velocity vector vertically, at this point we'd have a greater velocity vector, and at this point we'd have a greater velocity vector. And that's all due to the acceleration caused by gravity. So our minimum speed will be experienced here. Our vertical velocity will be 0. So the only velocity we'll be experiencing is the v horizontal, and that'll be 45 cos 30, which I will write down here, which is simplified to 38.97 meters per second. Now, part 5 of the question asks for the total flight time, which we already found out before to be 4.59 seconds. But what if I wanted to verify that with the equations of motion once again? Well, we can go ahead and use our equations of motion, and particularly let's go with v equals u plus at. So I'll write that down. And we'll go ahead and solve for t. We know that u, which is our initial velocity, is in the vertical direction, is going to be 22.5. So I'll put that in, 22.5. And I know our acceleration, which is a, is just going to be g, so that'll be negative g times time. Now what will our v be? What will our final vertical velocity be? Well, if you think about this, the velocity with which the ball is launched will be the same in magnitude to the velocity with which it will strike the ground. And that's because although our horizontal velocity doesn't change, our vertical velocity covers the same distance over the same time as it's exposed to the same acceleration on both sides of the flight path. So if I pick any point along this flight path, let's just take an arbitrary point like here. So let's say here and here. The vertical velocities will be the same, just acting in the opposite direction. So if I say I had a 10 meters per second velocity acting downwards here, that means a corresponding velocity acting upwards on this side, on the left side of the path. Therefore, our ending vertical velocity will be the exact same as the starting vertical velocity, just in the opposite direction. So I can go ahead and put that back into my equation, and I can account for the signs here. So I will say our final velocity, it's going to strike the ground with a vertical velocity of 22.5, and 22.5 will be negative because we've allocated up as positive. So let's go ahead and substitute all our numbers in, and I put that negative there just to account for the g. The g is actually 9.81, so let's go negative 45 divided by negative 9.81, and that'll give us our value for time, which is equal to 4.59 seconds. Now we can move on to part 6 of the question, which asks for the horizontal displacement at the end of the flight time. So there's actually two ways we can go ahead and work this out. We could just use the velocity equals displacement over time equation, which in our case will just be the horizontal velocity, which is v of h, is equal to displacement over time, and this x is r, and this t is big T for the total time taken. So we can plug in r, which is our unknown, vh, which is just 45 cos 30 times the time, which we know is 4.59, and that'll give us our range. So that'll spit out 178.8 meters. Or the second way we could work this out is by using the equation we derived before for the range, which is r is equal to v squared sine 2 theta all divided by g. So we can go ahead and plug in our values. So we can say 45 squared sine 2 theta, which is 60, divided by 9.81, which also gives us 178.8 meters. So let's move on to the final part in this question, where we're asked for the angle at which the ball strikes the ground. Now the angle at which the ball will strike the ground is just the angle between the two velocity vectors, just as it was for the angle at which it was launched. So let's go ahead and look at the velocity vectors. So we know our horizontal velocity vector is going to be the same, VH. And we know our final vertical velocity is going to be the same as the initial vertical velocity, but just in the opposite direction. So I'll draw that as VV, and that'll be negative of whatever this was, which was 22.5, but in this case it'll be negative. Similarly, we've got VH, which is just going to be 45 cos 30, so I'll put that in, cos 30. And what we want to find is the angle at which it strikes the ground. Now, from a bit of geometry, we can say that this theta is equal to that theta. So we can go ahead and work out that angle using the inverse of tan, or the tan inverse function. So we can say tan to the inverse of the vertical velocity component divided by the horizontal velocity component is equal to the theta. So if I go ahead and plug my numbers in, I should get theta is equal to tan. And remember, we're just concerned about the magnitude here, not so much the direction, because this is just a scalar quantity. So we'll go 22.5 divided by 45 cos 30, and that'll give us, surprise, surprise, an angle of 30 degrees. And which makes sense, because we've got a flight path that is entirely symmetrical. So this brings us to the close of this lesson. So as always, I'll catch you at the next one.